Hello everyone, my name is Robert, and welcome to a brief introduction to your electronics lab. Whether you're working in your garage, or in a state-of-the-art university lab, you are going to need some of the same essential equipment. You should all have some sort of lab kit, at least a bag of through-hole components, resistors, capacitors, transistors, etc., and a breadboard. Your breadboard will allow you to connect components in a number of configurations so you can build and test circuits. The breadboard consists of a number of strips like this, a grid of holes separated by a trench. All the holes on one line on one side of the trench are connected together. The connections don't go vertically or across the gap. The trench is primarily used to hold switches and chips. So as an example, these two resistors here are fine, connected like shown in the circuit, while this one is shorted, as shown here. Your breadboard should also have at least one power strip, a long line like this one. All the holes on one side of the strip are connected together. I find it generally best to connect the positive side to the red standoff on your breadboard's plate, and the negative side to the black standoff on your breadboard's plate. That way, you can usually connect to power via banana plugs directly to the DC power supply. Now that we've got the board and can build a circuit, we can talk about powering it to test it. Your DC power supply might take a different shape from this, but every lab should have at least one. The supply can be set to provide a constant, steady, direct current voltage to whatever circuit it is that you've built. A word of warning though, most supplies don't reset to zero when shut off. So it's a good idea to check the power level before you connect the supply to your circuit. Failing to do so will let out the magic smoke and set you back as you rebuild your circuit and find new components. When you are ready to start, make sure nothing is plugged into the power supply, then turn it on and adjust it to the voltage that you need. The supply will hold the voltage level between the positive and negative terminals, so that when you connect your lab to these terminals, you'll get the set voltage. Voltage is relative though, so if you hook your power supply up backwards, you will get negative voltage. Some labs will require multiple power sources of different voltage levels. When you use more than one power source, even in a connected power source like this one, you will need to tie those sources together, providing a common ground or point. If you don't tie your power supplies together in some way, the relative voltage between the supplies may not be what you expect. It is also possible to tie your power supplies together to create a common ground in the middle that leaves one supply as a negative. This is useful for certain circuits. Now that we have power, we'll need to measure it, circuit components, and their interactions. For this, we'll use a multimeter. Your multimeter can measure a lot of things. You will use it primarily for DC voltage, DC current, and resistance. It can also measure AC voltage and AC current, but usually only at certain frequencies, primarily those coming out of your house's outlet plugs, 50 to 60 Hz. To measure DC voltage, select the correct setting and plug the test leads into the appropriate sockets. Then touch the leads to either side of the component you are measuring. Keep in mind that the red port on the multimeter is on the positive end, and if you get it backwards, you may get negative numbers on your readings. Remember also that unless you have isolated a component, you will be measuring part of the circuit, so measuring resistance here will actually get you the equivalent parallel resistance of these resistors and not the lone resistor value you sought. To measure current, you will need to make two changes to the multimeter. First, move the red lead plug on the multimeter to the current socket, and second, select the DC current setting. You will also need to make a break in your circuit, since the current can only be measured with the ammeter in series with the circuit. The multimeter is a lot like a multi-tool in that it has a number of configurations that each do something different. And like a multi-tool, you will need to be aware of the configurations and settings so you don't attempt to measure voltage with leads plugged into the current setting. Failing to move leads or testing the wrong way will give you bad data and can lead you to blowing the ammeter's internal fuse. So now that you have a good idea how to create and measure simple DC circuits, let's say you want something more dynamic, like to see the rise and fall of an RC circuit. For this, you'll need an oscilloscope. The oscilloscope allows you to see oscillations or waveforms in your circuit's voltage. It's essentially a way to easily visualize changing voltage over time. Oscilloscopes can measure things like amplitude, peak voltage, frequency, and period of a wave. The scope can be set up to continually monitor a signal, or take a snapshot to show you sudden changes. Your scope will use specific oscilloscope probes. These connect with a BNC connector. To connect these, push the connector in and twist it clockwise to lock it in. It is important to note that these are locked on, and you cannot just pull them free like you could with banana plugs. Push in and twist counterclockwise to remove the BNC connector. The oscilloscope probe's other end should consist of a test point, or a spring hook, and a separate grounding wire, usually with an alligator clip. To measure something with a scope, we first need to make sure that the scope probe is calibrated. Locate the calibration points on your oscilloscope. Connect the ground clip on the oscilloscope to the ground calibration point and touch the test lead on the scope probe to the test calibration point. Most scopes will have an auto set or auto scale button somewhere on its face that will attempt to automatically scale and center the waves on screen. This button will never give you perfect results, but can often give you a good starting point for measuring. Find the button and push it now. We should get a picture of a square wave on screen that looks something like this. Now, if the corners of your wave look off, you can take a small screwdriver or alignment tool and tweak the scope probe to get them in line. Once this is done, you can connect your scope to the circuit by clipping the ground clip onto the grounding wire and putting the test lead where you want to measure the output. If you have multiple probes, you only need to connect one ground clip because the probes will share an internal ground. Each channel on the scope is represented by its own separate colored wave and has controls to manipulate them. The auto scale button will often separate the waves or place them at different scales, so you will need to move them around and resize them to get accurate comparisons. Signals can be stretched or compressed horizontally by adjusting the time per division scale, and stretched or compressed vertically by altering the volts per division scale. While all waves will share the same time scale, each may have its own voltage scale. With two or more signals, it is important to make sure their divisions in both waves are the same so you can accurately compare them. Some scopes will come with automatic measuring functions, allowing you to pull peak voltage, frequency, and similar measurements at the push of a button. Older models may only give you a set of moving bars that you will have to position yourself to measure your waveforms. Additionally, some scopes may have built-in math functions that allow you to perform other calculations, seeing the difference between the waves, or even generating a fast Fourier transform to see what frequencies make up a more complex wave. There is honestly a lot you can do with an oscilloscope, and I've only scratched the surface here. I recommend looking into the manuals and really doing a deep dive to learn everything that your scope can do. Alright, now that we've had a good look at an electrical signal, it's time to start making some signals that are more interesting than turning a switch off and on. For this, we'll need a waveform generator or function generator. These are often used in tandem with the oscilloscope to create various test signals to run through your circuit. Most often, this is used to simulate more complex signals your circuit might receive either as data or radio waves or something like that. A simple function generator can usually make sine waves, square waves, sawtooth waves, and duty cycle waves, which is like a square wave, but you can adjust how much of the wave is high. Function generators often default to AC signals, meaning that the voltage for the wave will swing positive and negative. If you don't want that, you will have to input a DC offset that can push them entirely above or below the zero line. Most waveform generators will also have an output on-off switch or button, so you can adjust the settings before you send the signal out to your circuit. Just like the oscilloscope, this device uses BNC connectors to plug in. Unlike the scope, they don't use probes, but instead will have a BNC cable going to alligators or mini grabber clips. We can test a signal from the waveform generator by connecting it directly to the oscilloscope, either by clipping the alligator leads onto the scope probe or by using a BNC to BNC cable. When we do so, we might come across something a little odd. The most common problem you will have here is that the peak voltage measured by the oscilloscope and the peak voltage set on the function generator do not match. The usual way of correcting this is by going into the settings for both devices and making sure both outputs are set to a high Z mode. Now, there are far too many versions of oscilloscopes and waveform generators for me to even attempt to explain how to do that here, so I'm going to recommend that you look up a manual. It's also important to note that your waveform generator is a separate power source, so if you're using it with a DC power source, the grounds for both, again, need to be tied together. Now, your specific lab may have many other items in it, like rheostat boxes or dedicated AC power supply, or fancier oscilloscopes that can handle signal generation work. Or your lab may have a virtual benchtop with a small breakout box and everything being displayed on screens on your computer or laptop. But it should at least have the basics we've listed here in one form or another. The best way to learn what these things can do is to experiment. Remember, your labs are here to teach you as much about the tools you will use for circuit design analysis as much as they are teaching you about the electrical components and concepts. I want to thank you very much for watching. I hope you have a wonderful time experimenting and becoming better with electronics. Please come back and see us again soon.